Good morning, everyone. My name is Goede, and this is Bryan O'Donoghue from Linaro. And we're giving a presentation about free and open source software support for MIPI cameras. So I'm a principal software engineer at Red Hat. I used to be a kernel subsystem maintainer for drivers platform x86. I sort of handed that over. I'm the backup maintainer now because I'm spending most of my time on the camera stuff. So I wanted to make more bandwidth for camera stuff. And yeah, then I'll let Bryan introduce himself.
Oh yeah. So I'm Bryan, as all of you know by now, I'm sure. I work in the Qualcomm Linaro landing team. I recently became one of the media maintainers is moving to a multi-maintainer model, so I started picking up some of the work to do pull requests for camera, media encoder, decoder, stuff like that on the Qualcomm side. I've probably been using Linux longer than some of you have been born. It's weird to me, even though I don't look that old, I'm told, but I'm actually 45. These are my GitHub where I put some of my work in progress and some of my handles here on IRC and Mastodon and stuff like that. I think the first slide is mine, actually. Yep. No. Oh, well. Do you want to? Okay, I'll go through this. So here's a brief list of topics we're going to talk about here. We'll try to assume nobody knows anything about cameras at all. I know probably most of you know more about it than I do, but we'll assume you're completely raw, and then we'll quickly move into more advanced stuff, and then we'll do a demo. Okay. So I've given this talk before, but I really like it because when I first came to do anything with cameras, I hadn't heard of Bayer. I mean, I'd heard of Bayer, but I'd heard of it as a name. I didn't really understand what it was or why it works the way it does. Now, most of you probably know that it's a pattern that effectively goes over the ADC that captures light. Most of you may know the reason that is done is because you obviously can't capture every single. Actually, your eye is more sensitive to green is the real reason. So when you are capturing light, if you think about it, if your eye is more sensitive to green, then the more of the color spectrum that you care about is in the green part of the spectrum. And in, I think, 1974, it says here. It should say that here. Yeah. Some of you probably actually know it's 1974. I had to look at the screen. Bruce Bayer comes up with a method to encode data in the Bayer format. And this is an example of a Bayer format here. And this is basically what we get out of the camera sensor on your camera. It doesn't come out as a nice formatted picture. It comes out in this kind of mosaic pattern that we call Bayer. Anything else worth really saying about this here? No, I mean, it's all on the slides. There are various different ways to recover the original data from a Bayer encoded image. Label, nearest, bilinear, Malar to Cutler. But effectively what comes out of your camera sensor is this. It's not a nice processed, nice to look at image. It's a mosaic. It's like something we'd find, under Vesuvius. It's cool to look at, but it's not making a nice picture. So, Hans goes next.
Yeah, so I got involved in this mostly because I'm part of the desktop team at Red Hat, and we want cameras to work on laptops. And laptop cameras always, closer to the mic? Yeah. So laptop cameras always used to be basically just USB camera modules with the standardized UVC protocol. So it pretty much just worked and we didn't have to worry about it. But unfortunately, these USB camera modules, the image quality isn't that great. There isn't really a technical reason for that. It's more just a budget thing or whatever, or laptop manufacturers never pushed the manufacturers of the modules to become better. So now to get a better image quality, Intel is pushing all the laptop vendors to move to the smartphone camera model, where you have like a roll sensor and then MIPI data transport to the main system on chip, and then the system on chip has a ISP to do a bunch of processing. Some processing also happens on the CPU or on whatever other blocks, and then we should get hopefully a better picture. So this is a problem for Linux on the desktop, because on the smartphone, your smartphone manufacturer, well, it's also an issue for Linux on the smartphone if you want to run regular Linux and not Android. But your smartphone manufacturer has some big blobby stack, which a whole bunch, a really big, lot of code and algorithms in there to make your Android phone give a pretty picture, basically. So yeah, so what's happening now is that we need to get these what we call MIPI cameras or complex cameras, because they're pretty complex. They have a deep pipeline with multiple processing steps and everything working under Linux. So we start with the raw Bayer encoded data, which needs to be demosaicked or debayered. And then after that, a whole bunch of other steps need to be done. So let's first take a look at what a hardware ISP does. So a hardware ISP is a dedicated processor, image signal processor, specifically for camera stuff. So it has a bunch of things hardwired in ASIC, so it can do things very power efficiently. It debayers. It also implements, the slide is a bit off. It says it implements the 3As, but it implements helpers to do the 3As. The 3As are very important for your image quality. So we have autofocus, which doesn't really have much of a focus at the moment on autofocus, because the laptop cameras have a fixed focus lens. What is important is auto white balance. I'll briefly show something about that in the demo later. And auto exposure. So the human eye is a pretty nifty piece of engineering, quote unquote, because we can see in almost dark, and we can see with the sun shining in our eyes, right? If we squint our eyes a bit. So computer vision has much more trouble with things like this, but at least we need to get what we call the exposure time right. So the exposure time is how long you basically measure each pixel cell, each monochrome cell, right? Because we have monochrome cells with the Bayer color filter on top. And if you measure it too short, then you get a very dark image. And if you measure too long, then you just get a fully whited out image. So if you get this wrong, you can throw all the image processing you want on top later on, but you just won't get a good picture. So getting your exposure right, and also your analog gain, which is another helper, which is especially important if you basically run out of exposure time, right? If you want to do 30 frames per second, you have 33 milliseconds per frame. So if you need a higher exposure time to get a good picture, you need to do something else. So you crank up the analog amplification in the sensor and analog gain to still get some sort of picture. So yeah, those are the 3As. The hardware ISP helps here that it gathers a bunch of statistics on the raw biodata. Usually histograms for like Y, so Y is luminance, and for RGB separately. And then you can look at those histograms and say like, oh, well, the peak of the histogram is way too dark, or it's completely on the white side, and you know that you have a whited out overexposed image or underexposed image, and things like that. There is also a whole bunch of other stuff happening. So very important is sensor tuning. I've actually just gotten into that myself, just as in it's been on my to-do list for a while. I wanted to maybe try and demo it here, so I started working on it last Monday during the conference. But surprise, surprise, I didn't manage to finish it. So one of the important things with sensor tunings is things like color calibration. So every sensor has a different color sensitivity for the 3 color groups. So you need to calibrate that. You also get some bleeding of say red into the green space, etc. You need to basically have a 3x3 matrix where you say like my real red value is this value multiplied the green pixel, and this value multiplied the red pixel, and this value multiplied the blue pixel, to correct for the bleeding and to correct for the curves and everything. So this 3x3 matrix we call a color correction matrix, and that is a big part of the sensor tuning. Other things are skin tones. So people are very sensitive to the color of skin. So if you get like, in theory, if you get your color calibration correct, you shouldn't need to worry about skin tones, but it still might be a bit off, so you can do some extra mapping there on top. And I know actually that some vendors do region-specific skin tone mapping, which may sound weird, but they actually, for me as an engineer, it feels wrong. Instead, I try to get the picture as color accurate as possible, but they have something like, oh, people like more white, more whitish skin tone in this region, so we'll fuss the skin tone a bit to make it more whitish. Yes, this is really happening. It's a bit unfortunate, and AI is making this worse, but yeah. Low light noise reduction, or in general noise reduction, but especially in low light it's important. So the sensor ultimately is analog, so you get analog noise, right? You get, maybe those of you who are old enough to remember analog television signal might remember the spiggly thingy in the dark area of the television. That is just what we call temporal noise. We call it temporal because it's time related, right? Your eyes mostly notice it because one frame it isn't there, and the next frame there the pixel is slightly brighter. And that sparkling effect is the temporal noise is the biggest issue. So there are like temporal noise filters in hardware, so which analyze over multiple frames and stuff, and those are all considered very secret by most vendors. So yeah, that's an issue for an open source implementation of complex cameras. And then there, of course, we have a lens. You probably have all seen like these fisheye lens shots, right? So that you have like a 360-degree vision lens, and everything is very distorted, right, because of the lens. But even these lenses, which are like straight on, they still distort. If you like point them at a checkerboard, it will still have sort of a fisheye effect. So you want to have lens distortion correction. Lenses are also have the problem that they're round, and your sensor is rectangular, so you get like shadows in the corners because the lens is less light sensitive there. So you also need like lens shade correction, we call that. So those are all the other things other processing steps which you need. So since it was, at least for me on the Intel laptops, very impossible to get the hardware ISP up and running with an open source stack. There is a closed source stack from Intel, which you can alternatively use on Fedora through RPM Fusion. On Ubuntu it's also packaged somewhere. So I decided that, well actually Bryan decided, Bryan was first. We decided, because Bryan wanted it for some ARM systems where there are similar problems with getting the ISP supported in an open, with an open source stack, that we needed a software ISP. So a colleague of Bryan, Andre, started working on that. And then at some point I came in and I sort of took over and did some optimization to make it run faster and did the final upstreaming of the software ISP. We demoed this as FOSDEM, not this FOSDEM, but a year ago. In the meantime, it has landed upstream, so that's great. And Fedora users actually can use it now. Fedora users with an IPU6 camera usually get a picture. It's not a great picture because we miss a lot of the processing steps from our previous slide. We don't have the sensor calibration, etc., etc. So long to-do list here, but we have this working and it works nicely at 30 FPS. What's new with the software ISP is we have CCM support now. So again, this is the 3x3 matrix, so you need to do 9 multiplications per pixel times full HD times 30 FPS is a lot of multiplications per second. So smaller ARM SoCs just, they go down to like 1 FPS or something if you try to do this. Even with our optimization, so we replaced the 9 multiplications with 9 lookup tables. So we could also squint black level correction into the lookup table and a gamma curve into the lookup table and a color cane into the lookup table. So we squished all those steps together, which is not ideal. It causes some precision issues. But it makes it possible, at least on a heavy laptop like this big Intel machine with a Core i5 or i7 or whatever it has, to do things in real time, right? So we can actually run 30 FPS here with the CCM. Unfortunately, we don't have a calibrated CCM yet. So once we have that, we should get a much nicer picture when it comes to color saturation and color accuracy and things like that. So yeah, then I will hand over the talk to Bryan again.
So Hans was just talking about the CCM, and what I'll tell you is on this laptop right here, the version of LibCamera, this is a Makena. I'm allowed to say Makena now. This is a Makena laptop, so it's a SC8280 XP from 2022. Am I getting the year right? Sounds about right. This is taped out 2022. So it's basically new. I mean, we live in a disposable society, but that's pretty new. It runs, so you can hook this up from your LibCamera to Pipewire, and you can run a video call in Firefox. So that's on an ARM laptop. That's a big achievement. I mean, it's trivial on x86, but for an ARM laptop, this is a lot of work. This takes a lot of fiddling about with the operating system and getting stuff to work. However, as soon as I switch on the CCM on this system, it's unfortunate the HDMI doesn't work. So it probably won't look great for the people on the other end of the camera, but I think you can pretty much see the frame rate here. So this is with the CCM and CPU. If I start this guy up again, Sod's Law says as soon as you try to do this in front of 50 people and whoever's on the camera, it won't work. But if you say it before you do it, it does work. And this is this is the GPU version of it running now. So I'll pass my laptop around. I think it's actually logged in as a demo user. So I trust you all. We're all friends. We're all friends, but just in case. So the cool thing is GPUs, as we've all come to know, are massively parallel pixel processing engines. Now, I started learning C++ in 2020. No, not 2020. What am I saying? 2001 or so, and 2020. Good boy, Bryan. And I thought I knew a little bit about OpenGL. I went through the NIHI OpenGL tutorials, and I had loads of fun drawing boxes. And excuse me, this is my missus calling me, so I'll just decline this. I'm getting in trouble now. You're watching me get in trouble at home in real time. Why don't you pick up the phone? So I had great fun writing OpenGL on Windows. So I came along to the libcamera stuff, and I spoke to Kieran Bingham, who's not here, and I said, "Oh yeah, I can take that on." So I sat in the meeting with Hans and Laurent and Kieran and Andre, and you know they're all really experts in the domain. So I was I like to think wise enough to shut up and listen for about a year and just receive and test their stuff before I tried to write any code. And I still very much defer to their expansive knowledge. I'm mostly just implementing things they suggest I should do. However, I did try, first of all, to take, I discussed this with Laurent extensively, what we were targeting for. So the first question you'll ask when you go to look at the code for this is, why is it all done in a fragment shader? And the answer is because we already have a fragment shader upstream. It already did debayer, and you don't throw away code, right? It's working code that works. We want to continue to have it work. There's time invested in that. There's intellectual capital invested in it. It's a real thing, so we want to continue to use it. So that's why we didn't go for a compute shader, and that's why we went for the lowest common denominator version of GLES we could, which it turned out to be is GLES 2.0, which I think I say here on the, yeah, so that's sometime around about 2007. So you should still theoretically be able to run I mean, if you can get something from 2007 to compile modern Linux, good for you. But at least in theory, the GLES component of this will work. And the kind of really interesting thing about it is that, good man, Pavel comes to deliver. Thank you, Pavel. So the first approach I took here is you can see that the diagram here has the soft IPA on the right. So libcamera is structured with two threads that run a soft ISP thread and then a soft IPA thread. And the soft ISP thread sends messages to the soft IPA thread to do magic, and it receives data back. And so the OpenGL version, the GLES version of the debayer system consumes exactly the same data as the CPU version. You know, this is a design goal. And, you know, whoever's going to rob my laptop, you know, wherever it's gone to, enjoy. But you will see that how did I get onto that? I don't know. I'm a suspicious person. But the point of it is that the soft ISP and the soft IPA, it's transparent to the soft IPA. We use a kind of interesting thing about the fragment shaders that were already there. And one thing that is different to how it's being done in Purism with the shaders you guys have is, of course, we need to consume CSI2 encoded data directly. And this is another reason that we reuse the fragment shader that was already there, because you have the 5 bytes and you have to sample through those 5 bytes and you have to keep sliding along that stream of bytes. So we have 2 fragment shaders. We have an 8-bit and what's called a 1x bit. So that does 10-bit and 12-bit encoded. It accepts the parameters that are supplied by the soft IPA. It applies those parameters and then hands back over to the existing software that Hans did to generate the statistics, the Bayer statistics. The really cool thing is the CCM is quite trivial that way, right? Because a fragment shader, the way a fragment shader works is you're effectively a thread on a single pixel. That's the basic model of which I didn't know when I started writing this. I was like, this be easy. I drew a triangle once in Windows. No, I mean this is a completely different way of thinking. It's like threads on steroids. Yeah, as you can see, it works fairly well. It's at version 2 on the libcamera mailing list. I felt motivated to send out a version 2 before I came here to speak about it. One really big problem that we had in the implementation was a thing called render to texture. So we get DMA buff handles, and the software contract, I hope I don't misspeak this now, the software contract from libcamera is you receive a DMA buff handle, and then you know what to do with that handle. That's the output frame buffer. So the first version of the GPU ISP, I couldn't get EGL create texture KHR and render the texture working. So I cheated. I asked an LLM, and I used GBM surface. So what you have to do with GBM surface then is you have to, why do you care about that? So GPUs do not store pixels linearly in memory as just RGB or RGBA data. They can compress it, they can tile it. So if you just read memory straight out of a GPU, you are going to get a garbled mess. You cannot give that out to another application to read on every single platform. Therefore, you must ask the GPU nicely to store the pixels in a format that works for you. There are a number of ways to do that. One way to do that is to use a GBM surface. So when you create a GBM surface, then you tell it to go into RGBA mode. Off it goes, and when it does its final write phase in the fragment shader, it will write a byte into memory, well, a word into memory. But as I discovered, if you do a thing called GL read pixels, it's extremely slow. It interpolates the data out of memory. It can take 10 milliseconds to read a frame. So that's no use. So what we had to do was use GBM surface to command the GPU to put it into a particular mode, and that's fine. But what you have to do at the end of the frame then is you must halt everything, and then you must mem copy out, and then unfortunately you must also invalidate the cache. So that's fast enough on a machine like this. When you start going down to the previous, these listed machines here, the TI Citara and so on, you're getting like 4 or 5 frames a second on a 15 frame per second machine sensor. However, once you get rendered texture working, it's all golden. It's extremely fast. Every single sensor we've tested so far, if it's a 15 frame per second line rate sensor, we get 15 frames per second. If it's a 30 frame per second line rate sensor, we get 30 frames per second, and that's applying the CCM on top. So I'm very happy with those results, and that means I'll stop developing now, and I'll start trying to push the patches and satiate all the people who are asking for unreasonable things like, please change the name, or please change the dot, move the dot 1 pixel left in your commit log. Please change your name to something I can pronounce. Things like that. What? It is upstream. We had an interesting discussion about benevolent dictators. I'll sideways here. We had an interesting discussion about benevolent dictators last night. And it was real benevolent dictators, how they would make the trains run on time in your country. And two of the people who thought benevolent dictators were great ideas were two of the upstream maintainers. Now, I won't suggest why that is, but it's just an interesting psychological outcome of the process. So the next steps for the GPU ISP, I personally am interested in denoising. There are some great examples in the Purism, what's it called, the Librem 5. The guys have done some great work there that looks like it could be stolen license permitting into the implementation we're doing here. We want to implement controls. So if you add a noise, if you add a means to denoise, you also want to be able to raise or lower your noise floor and have a little slider in your application to do that. So we will add some way of having the CPU ISP and the GPU ISP declare the kinds of controls that they can support, and then the application at the end will not be moving sliders for, say, denoising. We're not going to do that in the CPU. It's too computationally costly. Do you have another demo you want to do?
Oh, yeah.
Go. Yeah.
So we talked before about white balance and stuff. So what's interesting is, let me see what I have in here. Oh yeah, so I actually took a picture of a color calibration card, which I have over here. This is like a tiny card, which has a bunch of colors on them, and this costs 60 euros because the colors are really, really accurate. So you pay, I need to do math, but you pay quite a lot of euros per color. But I took a picture of it, and we also have some open source tuning tools, mostly thanks to Raspberry Pi and libcamera. So I was hoping, because I actually took this picture here in this room because I wanted to have the CCM for this light. I was hoping I could get a CCM out of it, but if I run the soft ISP calibration with lib tuning, it says the Macbeth patches, those are the names for the little colored squares, are saturated. So apparently I need to tune down the gain a bit because it's complaining the white is too white, it's oversaturated, right? It's fully flared out, flamed out. So yeah, unfortunately, very close. This was like 5 minutes before the talk was starting. So some of you were early, might have seen me messing around with stuff. So yeah, very close but no cigar, but I can still show something somewhat interesting, I think. So if I run QCam over here, this is like the latest Git checkout, but I actually disabled the software ISP because I needed to get raw buyer for the calibration stuff. I can run, but QCam already had debuyer shaders, right? The first debugging support in libcamera outside of hardware ISPs were actually the shaders Bryan reused from QCam, which is a viewer app. So this does debugging, but it doesn't do white balance. So it looks a bit greenish. And if I now run with the software ISP, because I don't have Bryan's branch with the GPU ISP here, but the result should be identical, then it looks much better, right? So this does black level correction, and it does very basic white balancing, just 3 color gains, but it already makes a significant difference, right? So yeah, and look, image out of a MIPI camera on an x86 laptop. And it even works in Chrome and stuff, like if you want to do a video call through PipeWire. Thanks to lots of work from my colleagues, Wim Tijman and especially Jan Grulik, yes, Jan Grulik, thank you. He did all the work on the libweb RTC, which is the shared web RTC implementation between Firefox and Chrome to get it to support PipeWire as a camera source. Which is also nifty, so now you can be in a video call and then you can open a camera, the GNOME camera app, and then see the camera at the same time. Because PipeWire allows duplicating the frames, but yeah, that's a bit off topic. But yeah, so that was my little demo about the white balancing in the software ISP. Unfortunately, no color correction matrix support yet. Should have started earlier than Monday, but yeah. At least now I've gotten over the initial hump, right? A conference like this is a good reason to I really need to start working on this, but I have so much other stuff. So yeah, you probably all know how it works. So I've gotten past the initial bump, I'll go and try to get it done.
This one here has an identity CCM, so everything is set to 1, but it's still a legitimate test case, right? Just so you know. It's not calibrated, but it is doing something.
You can just ask GPT for CCM and it will give you one, and it will look way better than this.
You can just ask GPT for a CCM, it will give you one and it will look better. Okay. Yeah, it's an interesting experiment, but I'm not going to do it right now. So, yeah, we indeed have arrived at the questions part of the talk. How long do we have?
It is 31 minutes past 9.
Ah, so we actually have like 8 minutes for questions. That's great. So, any questions? Oh, yeah, sure.
What's the speed of IMX8?
What is the speed of IMX?
On an IMX8
8.
for the GPU ISP?
Did we run that? Do you know?
So on the Citara, so we were Milan Samal, who's not here, but he's done so much work on this. He deserves to be called out. He has been running on the IMX8, but then he switched over to the Citara, and I don't know if I wrote it down here, but I should have. Oh, look. Oh, it's all here, right? So it's 15 frames per second on the Citara. So what I will tell you is I have another platform called it. Yeah, actually it's up here. Right? I did write it down. The SM8250 RB5. With the CCM, I get 2 frames per second. So with lib camera, as I receive it on Debian, whatever I'm running on that board, I think it's not. I think actually I've compiled 0.5.2, but I'm certainly getting 0.40. I get 25, 27, 30 frames per second with the CPU ISP. As soon as I put on the CCM, it drops to 2 frames per second. And I've even included some parametrics here. And so what you can see is the core goes over 100%. Now, I've never actually really understood how Linux reports more than 100% on a single core. I mean, my maths maybe isn't great, but over 100% just doesn't seem true. However, I know somebody knows, and they'll tell me later on. But it reports over 100%, 106%. As soon as we switch over to render to texture, so my motivation for getting render to texture working was that the implementation I had for GBM Surface didn't run at 30 frames per second on the SM8250, which is a processor from 2019. And that's when I knew that, maybe I didn't care about IMX8, but if I couldn't even run it on a Qualcomm chip from 2019, it was definitely a performance problem. So I don't quite know what we will get on the IMX8, but I'm pretty sure you're going to get line rate for anything reasonable. I wanted the test before the conference, and I claim the kudos. I bought the board, which is 90% of the work. So I'm 90% sure you'll get line rate. But no, I haven't had the time to bring up the IMX8. But because it's ubiquitous, it's important to know what rate this will run at ultimately. Yeah. I think we had another question. Introduce yourself, young man.
Hi, I'm Tristan. So, awesome work. I really like what you did. I just have kind of sad feelings that we put this expensive ISP to the mobile phones, and we basically don't use this hardware. But on the other hand, on the processors like MX8, which don't have the ISP, the GPU is not powerful enough to use it, right?
I welcome every single vendor who is going to invest the time to enable an ISP. It will still be the case. Not all of them will, and it's still valid work to have out there in the open source community. So please do accept the challenge, the throwdown to upstream your ISPs, various vendors. It's still work that's going to be useful to people for the foreseeable future. So
Yeah. For the hardware ISPs, we do really want to get them upstream, but there is it just even if the vendor cooperates, it just also takes a lot of time. So I think the software ISP, especially the GPU version, especially once we have it like up to a somewhat higher image quality, will be very, very valuable just for initial board bring up, right? So you only need to do the CSI2 receiver, and then if you already have a sensor driver, like bam, you have a working camera, which is really nice. But yeah, we definitely want vendors to cooperate with upstream kernel, with upstream lib camera, and get their ISP supported upstream. So yeah, go for it. What else did I want to say about this? Oh, yeah, I think it will also be valuable as like a baseline. So one of the discussions you have with vendors when you talk about supporting their ISP, they may want to like support it partially, but they say, yeah, these and these blocks are very secret. So we don't want to support those upstream. At least then we can point at like we have it in an open source software ISP implementation. So you should be able to also open your hardware version, right? So it will also sort of serve as a baseline. At least that's my personal vision of how I hope this will work. So yeah, there was a question here.
Yeah, this is continuation of the previous question. Since all the work you have started and pushed upstream, did some vendors, so for example for IPU6, did Intel contact you, try to make things move forward?
Yes, we are in talks with Intel. They have something of a plan to get their IPU7 ISP supported upstream. But yeah, we're still waiting for them to post like a V1, but they have something of a plan. They have some sort of concept which they think might be acceptable to the community. So we need to get to the point where they post it upstream. And then, we sort of, for the ISPs, we want to use the same rules as in the DRM subsystem, which basically is that there needs to be, you cannot just throw a kernel driver upstream. There needs to be a working open source user space implementation, which, as the DRM documentation says, is not a toy, right? I mean, with DRM, it's easy. You can say you must implement at least OpenGL4 something or whatever if your hardware is capable of that. With ISPs, it's more complicated when it's not a toy because, yeah. Again, this is where the software ISP might help as at least like a minimum baseline. Like if you're worse than a software ISP, then you're in the toy category still. But that won't be the final verdict, though, right? It won't be that's what you need to do, and that will be a negotiation with the community. So I know Intel is looking into this. I cannot say a whole lot more about it. I hope they will continue on this path. It would be cool if we could get like a semi-big vendor like Intel. I mean, they are a big vendor, but in the ISP world, they're not as big as some others. Then also we have one more example, right? We already have the Mali ISP, and we have the Rockchip V1 ISP, and Raspberry Pi is doing, I really want to give a shout out to Raspberry Pi here. They're doing great work with an open source camera stack, right? They have, everything is open what they have. I mean, their custom distro runs a fork, but that's mostly just because it takes a lot of time to get everything upstream. And also sometimes, I mean, everyone feels the need to balance like being upstream versus shipping features, right? So they have a bunch of camera features which may need more rework inside Lib Camera, which they're shipping in a version which may need to change before it can go upstream. So they have their own forks, I believe, which they ship, but which are very feature rich, but it's all out there, it's all open, and they are working with us to get it upstream, and they're piecemeal. So yeah, really big shout out to Raspberry Pi here. But we need, I think if we have one or two more examples of hardware ISPs in the kernel and Lib Camera, then we can really start telling other vendors like, those folks can all do it, so you should be able to do it too, right? Any more questions?
No more questions? The more questions, the more chances you have of winning the raffle.
How modular is the camera? So let's say I do have some hardware that can do dewiring, but then I want to use your graphics or signal.
At that level, at the moment, I would say it's not very modular. We do try to recognize common code. So we have something which is called pipeline handlers, right? So hardware ISPs are very complex. And basically, you cannot just try to generate code which does the topology configuration, the topology configuration of the ISP, etc. Needs some platform-specific knowledge. So that's all put into what we call a pipeline handler. There also is an IPA, an image processing algorithm plugin, which belongs to the pipeline handler because the statistics which the IPA consumes are ISP specific. And also the sum of the parameters it generates back to the ISP for the next frame are also. So at the pipeline handler level, it's pretty modular. And if we notice that certain blocks of codes are shared between multiple pipeline handlers, then we do try to push them to helper libraries. But it's, I mean, once we get like one of these added to say the software ISP, then reusing it will require some refactoring basically to use it in your own pipeline handler, like pushing it into a library. That's just something which we need to figure out as we go, right? Right, I think at the moment the most important thing is get the V2 or V3, V4, or whatever, what Bryan did upstream.
Definitely V3. It'll be merged.
And then build on top of that, right? And then I mean, as long as we don't, I mean, lib camera even has the liberty to break the API to applications with consume lib camera, but we try to be a little bit careful there, I believe. I'm looking at Laurent now. But if necessary, we do break the API if we have the feeling we have to. We're not as strict as the kernel to user space API there. But especially as long as you can do refactoring without breaking the API to applications, it's all fine. It's basically the same rules as in the kernel, right? Except that the kernel, there's like a hard point where you cannot refactor when it causes user space API changes. And in libcamera, we can even do that. We do require applications to adapt over time. Because we're still so new, basically, that we still need to get to a point where maybe we will say we'll do an API freeze, or maybe we do like a 1.0 branch which is API frozen and the default branches. We'll figure it out as we go.
But is the goal to be able to use the GPU for post-processing with a hardware ISP, but we lend that for full SAP GPU ISP first, and then let's see how it
Okay, so I just heard that you get bigger chances in the raffle, which if you answer questions,
You get good karma.
you get good karma, right? So any more questions? Well, I guess we're also.
Slightly unrelated question, but most of these devices seem to use Sony cameras on the sensor side. Do you have a good idea how to get proper data sheets for that?
I'm going to defer this. I'm going to defer this to Laurent because I think he might actually know.
Sony booth downstairs and ask them? Yes, that's right. For 20 years now.
That's the right answer, by the way.
By the way, the response seems to be that other vendors are not much better.
Yeah, that's definitely true. Also, my experience with the data sheet is it gives you, like, this register has this name, and maybe these bits in the registers have these names. This is all the info we have for you. Good luck.
They don't